Hello and welcome back to this course. So this lecture is about the relationship between neurons and the human brain. So this is basically what our brain consists of. It consists of billions of neurons interconnected, and each neuron is passing a message to another neuron, and at the end you have a specific action to be performed. So let's say, for example, you want to reach your pocket to grab your wallet. So there's a command that's being sent to your brain, and now then this command basically gets passed to the neurons in your brain, and then the neurons that are dedicated for this command gets fired up, and at the end the outputs of all of these interconnections will send a command to move your hand and grab your wallet. So what we're going to do here is we're going to model this mathematically. So before we do this, let's explore the neuron. So the key to artificial neural networks is that their design enables them to process information in a similar way to our own biological brain. So they were made as a mathematical model that mimics the human brain. So they act the same way, in a very similar way. I'm not going to say the same, but they act in a similar way. So basically, just like the human processes information, we're going to mathematically model this and turn this into a neural network that's able to process information in a similar manner to our brain. So our brain consists of billions of interconnected neurons. Now let's have a look at this neuron right here. So we have the inputs here to this neuron. So this is a neuron right here. This whole thing is a neuron. And we have the inputs to this neuron as the dendrites. So the dendrites are required to collect the input and feed it to this neuron. Now, this neuron either fires up or not. Now, if a neuron fires up, that means this information it received from the dendrites is important, and depending on the importance of this information, this neuron fires up or doesn't fire up. So if the information is important, then it fires. If the information is not important, then it just doesn't fire. So when it fires up, it sends an electrical signal to the boutons. Now these boutons basically pass the output to 1,000 of other neurons. So that's how it works. You receive some inputs, and if these inputs are important for the specific task, then this neuron sends another output to the boutons, which also is, these boutons are networked to thousands of other neurons. So that's how the information is passed throughout the brain. So a very nice fact, this is the reference for this fact, which is made by Paul Reber. Now, if your brain worked like a digital video recorder in a television, then 2.5 petabytes would be enough to hold 3 million hours of TV shows. So basically, if you would have to leave the TV running continuously for more than 300 years, then you'd use up all of that storage. So this is how much memory our brain contains. Basically, billions of neurons. So that is the relationship between neurons and the brain. Basically, a neural network or an artificial neural network is a mathematical model of the human brain, and that's why it's called an artificial neural network, because it was made artificially. So if we recall, this is the neuron. We have the dendrites, which basically are responsible for receiving the input and passing it to the neuron. And then here we have the output of the neuron that is getting passed to the boutons. So this is exactly what's happening here. These are the inputs that we have, okay? And these here are the weights. So these are the dendrites in this case. Now each input is going to be multiplied with a weight, and then we're going to sum everything up. And after that, we're going to pass it through an activation function, and this activation function is going to be responsible whether to fire this neuron or not. And then this output is passed to the other neuron. So this is exactly what's happening right here. Again, these are the inputs, your dendrites are the weights, this is the neuron, And then we have an activation function that decides whether this neuron should be fired or not. So this is right here. And at the end, your output gets passed to the other neurons, which is right here. So each neuron receives the net input value, which is coming towards it. So this neuron receives the input from x1, x2, x3. Now we also want to multiply the input with a weight. So these weights give importance to your inputs. Now here we have 3 inputs, or you can say 3 features. And definitely not all features may be important. So we might have a feature that is more important than another, or a feature that is less important. So a weight gives an importance to each feature. So we're going to take each feature and multiply it with a weight, and at the end we're just going to sum everything up. So this is exactly what's happening here. All of the inputs are summed up. And then we have an activation function that decides whether this neuron should be fired or not. And in this case, we're just going to use the basic sigmoid activation function, which squashes your output to a value between 0 and 1. And then you have your output. Now, I'm just showing you how we convert this biological neuron to a mathematical model. But of course, we're going to talk much more in detail about this whole thing, about the artificial neural network, about the weights, how they learn, and everything in the next coming lectures. So don't worry if you don't really understand right now. So the sum here is x1 multiplied with its weight, so x1 times w1 plus x2 times w2 plus x3 times w3. So all of the inputs multiplied with the weights, and we're going to sum them up. Then we're going to pass this result, the summed result, to an activation function. So in this case, we're going to use a sigmoid activation function, and what it does, it just squashes the output to a value between 0 and 1. So this value after the activation function gets passed to the other neuron. So this is exactly how we can model this neuron. Let's take an example. Let's say that we have these 3 features, negative 2.1, 1.2, and 0.6. And let's say we have these weights for each feature. So we're going to multiply each input with its weight. So negative 2.1 multiplied with negative 0.2. And then we're going to add it with the second feature times its second weight. So 1.2 times negative 0.1 and 0.6 finally multiplied with 0.6. And at the end, you're just going to get 0.66. And then if you pass this net input value to your activation function, so this is the mathematical equation for the sigmoid activation function, 1 over 1 plus e to the power of negative z, where z is your net input value. Okay, so if we plug in the z here, in this case the z is 0.66, so 1 over 1 plus e to the power of negative 0.66, we should get a value between 0 and 1, because this is what the sigmoid activation does. In this case, we get 0.659. So this is the output, and this output tells whether this neuron should be fired or not. So in this case, it seems like it has a high value, so definitely this neuron might fire up. I'm just giving you an example. And again, we're going to talk about the activation functions in a separate lecture. So whatever we're saying here, this is just the basics. This is just to deliver the idea of mathematically modeling a neuron. But definitely, all of the concepts, we have a separate lecture for them. So we're going to speak in detail about them. So if you realize what's happening here, this is an equation of a straight line. What we're doing here, z equals to x1 times w1 plus x2 times w2 plus x3 times w3 and so on. This is just the equation of a straight line, which is y equals to mx plus c. Okay, so y equals to mx plus c is the equation for a straight line. Now here we have a bias. A bias is just an extra weight that is always multiplied with 1. So the feature value for the bias is always 1. And this basically allows the neuron to fire up if needed. If these weights with their inputs don't really help the neuron in firing up, then this bias does. So we're going to add a bias term. And now realize what happens here is that we have an equation of a straight line. So B here is your C, and your inputs x1 w1 plus x2 w2 plus x3 w3 is just mx in this case. But of course, here we have only one feature. Okay, so in this case, we have three features. It's basically just multiple features. But if let's say we only have one feature, so we'll have z equals to x1 w1 plus b. Okay, so in this case, x1 here is x, and w1 here is m, and c is b. Okay, so this is when we have one feature, but here we have three features, so we have this equation right here. So this is the equation of a straight line at the end. This is what's happening. And we realize that this perceptron may be able to separate the inputs by a straight line. So we have two classes, and using this equation, we're able to separate the inputs by a straight line. So we can classify between these two classes, which is C1 and C2, using this perceptron. Now, what's the limitation of a perceptron? It's only capable of separating data points with a single line. Now, what if the inputs cannot be separated by a straight line? What happens in this case? This is where we arrive in something called the XOR problem. And this is how the multi-layer perceptron was derived. So if you take the AND gate, now realize that the AND gate, if you recall from high school, is just a multiplication of your two inputs. So you only have an output of 1 when your two inputs are 1, or when there's a non-zero at any of your inputs, then you have a 1 here. This is the AND gate. So when your two inputs are 0, 0, you get an output of 0. When your two inputs are 0, 1, you get an output of 0. When your inputs are 1, 0, you also get an output of 0. And now when your inputs are 1, 1, then you only get an output of 1. Now if we plot these points right here, we can see that these points are able to be separated by a straight line. Okay, so the perceptron is successfully able to model the AND gate. So here we have two different classes. The first class is 0 and the second class is 1. And realize that we can separate these two classes, which is the 1 and the 0, from each other using a straight line. That means that the perceptron is successfully able to model an AND gate. Now the same exact thing happens for an OR gate. A perceptron is able to model the OR gate because you can separate the two classes, which is 0 and 1, using a straight line. Okay, so in this case, we have two classes. The first class is 0 and the second class is 1, and they are capable of being separated by a straight line. Now, if we look at the XOR, so recall again from high school, XOR gives you an output of 1 when your two inputs are different, and gives you an output of 0 when your two inputs are the same. So here we have two inputs which are the same, 0 and 0, then we get an output of 0. And similarly, 1, 1, two inputs are the same, so we get an output of 0. Now when your inputs are different, so when you have 0, 1 or 1, 0, then we get an output of 1. Okay, so if we basically plot these inputs right here, now we can't really separate the two classes by a straight line. We're going to need a curve to separate this. So we're going to need a curve that goes like this, okay, in order to separate these two classes, which is the 0 class and the 1 class. So there's no single straight line that is able to separate the two classes, which is the 1 and the 0. Therefore, they're not linearly separable. And this is where the multi-layer perceptron comes in hand. So when we're not able to separate the classes by a straight line, then we cannot use a single perceptron. We're going to have to use a multi-layer perceptron. Okay? So a single perceptron is not sufficient to model the XOR problem. Therefore, the solution is to expand beyond the single layer architecture by adding an additional layer of units called the hidden layer. So this is the hidden layer here. And sometimes it's called the processing layer because it basically processes your inputs, and then this processed results gets passed to your outputs. So this kind of architecture is called a multi-layer perceptron, or MLP for short. So again, we use a multi-layer perceptron when we can't really separate two classes by a straight line. Now realize that most real-world applications are not linearly separable. So basically, an MLP is the basics of deep learning. So what are deep neural networks? You should guess by now. Basically, it's just a neural network with many inputs, several hidden layers with several units, and an output. Okay, so this is an a figure of a deep neural network. You have your inputs. You have several hidden layers. Here, for example, you have 3 hidden layers, and each hidden layer has several hidden units in it. And at the end, you have an output layer, which performs your prediction or your classification, depending on your task. So the number of output neurons or output units depends on the classes we want to predict. So if our task is to predict whether an image is a cat, a dog, a bird, or a cow. So in this case, we have 4 classes to predict. So we have 4 neurons in the output layer. Okay, I'm just gonna say output neurons in this course rather than output units. However, they're exactly the same thing. I just prefer to use output neurons. So in this case, we want to predict 4 classes. Therefore, we have 4 output neurons. So this is a figure of a deep neural network, or in other words, a deep multi-layer perceptron. Thank you very much, and that's it for this lecture, and I'll see you next time.